Photoelectric Effect by Zain Shahzada. For some time starting from the 1800s, we knew light to behave as an electromagnetic wave. Light has wavelengths, expressed by a lambda symbol, and they have frequencies, expressed by the fancy F symbol, both which are inversely proportional to each other, meaning the shorter the wave the higher the frequency, and longer the wave the shorter the frequency. Both are related by the equation c is equal to lambda times frequency, where c is the speed of light being 300 million meters per second, the fastest thing in the universe. The electromagnetic spectrum outlines light of all different wavelengths. This spectrum shows us the wavelengths of gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves. Between ultraviolet and infrared light, there is a type of light that we call visible light. We can detect the light present in the spectrum with our own eyes when we look around our various surroundings. The development of the wave theory of light was useful and helped shape the understanding of the universe, but it was unable to explain a phenomenon called the photoelectric effect. To understand the photoelectric effect, we need to know that metal contains electrons that are free to move within the metal. The electrons are attracted to the positive charges of the metal atom nuclei. This in turn means that energy is required to remove the electrons from the atoms of the metal. The minimum energy required to remove an electron from a metal is called the work function. Researchers usually give the value of the work function in electron volts rather than joules. Shining light onto metal is another way to remove electrons. If an electron absorbs energy from light striking the metal surface, and the light energy is above the work function, the electron could be ejected from the metal. This observation is the observation that is known as the photoelectric effect. Experimental studies of the photoelectric effect showed that electrons cannot be ejected from the metal unless the light is greater than a specific frequency. This frequency is called the threshold frequency. It is the minimum frequency required for light to eject an electron from metal. Physicists were not able to explain such a phenomenon with the understanding they had for the theory of light at the time. One of the reasons was because according to the classical theory of light, the light wave that carries energy is proportional to the intensity of the light, meaning it should be possible to eject electrons by increasing the intensity to a high magnitude. But experiments showed that no matter how great the intensity when the frequency is below the threshold, electrons won't be ejected. Another reason was that the classical theory of light predicts that the electron's kinetic energy will increase if the light intensity increases. This was not the case, even though the kinetic energy of an electron is independent of the light intensity. The photoelectric experiment allowed scientists to test the wave model against the particle model of light. For this particular setup, scientists had control over both the intensity of the light and the frequency of the light. Scientists were able to independently vary one experiment over the other, and note the effects, enabling scientists to determine the appropriate model for the system. Observations observed by the scientists supported the particle model of light. It was postulated that beams with higher intensities contain more photons. As a result, higher intensity beams eject more electrons, because more photons are present to transfer energy. However, that is not the case. The amount of energy one photon can transfer to an electron is determined by the photon's frequency. Increasing the frequency of incoming light increases the energy transferred to the electron, which is why higher frequency beams produce electrons with more kinetic energy. In addition, Einstein, with his quantum theory of light, believed that photons carry parcels of maximum kinetic energy. Einstein's theories explain two puzzles with regard to the photoelectric effect. When energy in photons is less than the work function of metal, electrons are not able to escape from the metal. For monochromatic light, increasing the intensity increases the amount of photons arriving each second. However, if the energy brought by photons is less than the work function, electrons will never be ejected no matter how much the intensity increases. The event of an electron being ejected depends on frequency, not intensity. Second, Einstein's theory of light also states why the kinetic energy of electrons depends on the frequency of light. The threshold frequency related to the photoelectric effect corresponds to photons whose energy is equal to the work function. So that means a photon with higher frequency and thus greater energy is able to eject an electron and pass on excess energy. This is what the wave model of light cannot explain, but the particle model can.